I think I heard Noah say you thought A didn't belong, right? Why would A not belong?
Because everything else is relatively straight line.
Yeah, because everything else is like real tight. I can see definite shapes. And one's real floofy. Is real loosey-goosey. Okay, so that is an absolutely valid reason on why it might not be A. Or why A might be the one that doesn't belong. Anyone pick something other than A? B? D. Why maybe D, why would D not belong to something? Yeah, it's going downwards. So it's vaguely kind of like this downward slope. Everything else is kind of going up, kind of vaguely going up. So everything else is vaguely trending positive. That's the only one that's vaguely going negative. What else do we have? C. Why might C be something we'd say doesn't belong? The dots are different? Yeah. You're not wrong. You're not wrong. What might be kind of another way we can say that? What might be something else that's different on that? It's not quite what I was looking for, but you're not wrong. Yeah, it's got a curve to it. Everything else is kind of line-based. But C has a definite, like, Nike swoosh to it. That's okay, and so then our last one, B. Why might someone pick B?
Because there's a dot and like out of.
Because there's a dot that's way off to the side. It has an outlier. Okay, so it has an outlier. So there are legitimate, no joke, valid reasons to pick each one of these as something that doesn't belong. But we have a reason why we picked it. So we have data to back up our opinion, basing our opinion on something tangible, something valid. Okay, we're not just going on A because I don't like it, or B because it's my initial. Just saying. So we have reason, we have data, we have something for which to back up our opinion. So I handed you guys your papers back from yesterday so that we could kind of talk through them because I wanted us to be able to talk through some of these. So I'm going to put them up on the screen. There it is. All right. So here was A, our divorce rates in Maine versus our per capita consumption of margarine. Do these have a correlation? Does their data move together? Yes. Yeah. Their data moves together. There is correlation between the data points. Is there causation here? Does the divorce rate in Maine have anything to do with the U.S. consumption of fake butter? No. Because that's like that's not even the same population. That's the U.S. consumption of butter and divorce in Maine. I could not even think of any reason at all why those could be in relationship even a little bit. Except for the fact that they are surprisingly similar graphs. But other than that, that's all they have in common. So yes, there's a correlation, but there is definitely not causation here. What about something like B? What did we think about here? Doesn't really make sense? It really depends on the population you look at. Because I agree, if we look in this room, this don't make any dang sense. If we look across all students in Pike Township, everybody, could we see maybe another reason why they might have a relationship? What else could cause students with larger shoe sizes to be better spellers? Their age. Your feet are definitely bigger than a kindergartner's feet. You are also a better speller than a kindergartner. I hope. But that's not being caused by your feet. Your spelling capabilities are not being caused by your feet. So age is another contributing factor. So yeah, there's probably a positive correlation here, as long as we're looking at a big enough population. So again, if you looked at just people in this class, I agree with you that there is not a correlation or causation. If we look at a bigger population, there's probably a correlation. There's still not causation. It's not your feet causing you to spell better. There is now a Broadway song that actually makes reference to this, and it's just popped into my head. But it's not your feet that are making you a better speller. It's the fact that you got bigger. So it's things like that. There's a couple in here that are really kind of fun. Some of my favorite graphs are in here. Cheese consumption and people who got tangled in their bed sheets. Again, surprising correlation in data. Do they have any relevance to each other? No. No, it's just a funny graph. In fact, most of these graphs were just amusing because I find them very amusing. They're some of my favorite things. How about carrying umbrella with rain? I think there's a correlation. A forecast of rain.
Oh,
Yeah. There probably is a positive correlation. The higher the likelihood of rain, the higher the chances someone's carrying an umbrella.
yeah.
Assuming people look at the forecast. Okay, I'm not saying everybody carries an umbrella on the day of rain, but there's a probability. So some of them are really clear like that. Some of them are a little bit more deceptive. E was one that was a little bit debatable. And this is one that a lot of us talked through, and I know I talked through with this one with a bunch of people, is this talks about children who receive tutoring have lower grades than those who don't. Do you have to have a low grade to get a tutor?
No.
Do you have to have a high grade to get a tutor?
No.
Does the tutoring have any relevance to what your grade was? No. So there's not really a correlation here. If they talk about changes in grade, we would hope that people who had tutors might have an improvement in their grade, but that's not always true either. So sometimes our instinct says, oh, yeah, tutoring and grades, those are going to have a relationship. But if we think through the logistics of it, it's not necessarily true. This is another one here. We've got as sunglasses sales increase, the rate of ice cream sales increases. Does that make logical sense that those have a correlation? Are the sunglass sales, though, causing the ice cream sales to go up? No. What is probably an outside factor that's probably helping both of them? Heat. The heat outside. So they have a positive correlation, but they do not have cause and effect on each other. They don't have cause and effect on each other. It's not sunglasses sales that are causing ice cream sales to go up. And ice cream sales are not causing sunglasses sales to go up. So it's like that on a lot of these things. The graphs are fun. This is one of my favorite graphs because there's a surprising match in the data between the number of films Nick Cage appeared in and the people who drowned by falling in a pool. Nick Cage is neither causing people to drown, nor are people drowning causing Nick Cage to be in movies. That doesn't make any dang sense whatsoever, but their data surprisingly lines up pretty good. Okay, so most of these graphs were very, very silly because they make me very, very happy. I love misleading graphs. They're fun. I have too much fun with that. Okay, so what we're going to do today is we're going to look at pages 93 through 95 in your book. And what we have here is a lot of information about a car. We've got Jane here that wants to sell her Subaru and she wants to sell it herself. She doesn't want to take it to CarMax. She's going to sell it by putting it up on Facebook Marketplace or on Craigslist or whatever. So she wants to get a good price for it, but she also knows she doesn't want to underlist it or overprice it. So she's trying to find the right price for her car. So she got this list of cars that are the same model as hers that have sold recently. They have different ages, they have different mileage. So we've got this information for some cars. And what we're going to do is we're going to try and find an equation to be able to calculate what she should price her car at. And so you have this table. And what you can do is if you go on Canvas, I've given you this data as a shock of all shops CODAP file. So if you go on Canvas, on today's page, there's a link to this CODAP file. So I want you to take a couple of minutes and see if you can come up with ideas of pairs of information that might help us figure out how to price her data. See what we can come up with. What might help? And this little text box here actually gives you a whole lot of questions that are in the book. If you go on the Canvas page, there's a link to this CODAP file. So I'm going to say it's going to help us probably to have a graph. I'm going to move these words because I don't really want the words. I would like a graph here, and it might help for us to have a couple of graphs. What information is going to be helpful for us to be able to use? How could we try and find the relationship with the price? What sets of data might we want to pair up? So I want to know how the age relates to my price, and I want to know maybe how the mileage relates to my price. So I'm going to make two separate graphs. I'm going to take my age, I'm going to put it on my x-axis, not for any particular reason, I'm just picking it. Now I'm going to put price on my y-axis. And it gives us a kind of scatter plot looking thing, which is cool. But let's also see what's going to happen if we check our mileage versus our price. So I get another scatter plot. What we're going to try and do here is we're going to try and find a line of best fit. You've probably heard that before, that phrase. So what we're going to do is on our graphs, what you have, the ones you have there, you should hopefully make those two. In the ruler, I want you to click on movable line. Close that. And I want you to kind of move these dots around and see if you can kind of figure out a line of best fit, what you think is your line of best fit for the data. And you can move the yellow box like out of the way. It's kind of annoying. I mean, you don't want it to fully disappear. I'm not sure where mine went. But if you like slide it out of your way a little bit, you can access your dot. And I want you to do that for both of your graphs here. See if you can find your best fit line. That yellow box has the equation for your line in it that you can see. And you can do that on both lines. The graph's a little bit bigger. we can get kind of close on these equations. We're making a guess on our best fit line. We could write these equations down and use them because we know how to do that because we're good and awesome at math like that. But we don't know if this is the best line yet. So there's a way to have CODAP help us. Shock. I know, right? And what we're going to do is you're going to go into your graph and back in that ruler, what you're going to do is you're going to hit the least squares line. And that'll show you how close you were to the actually bestest of the best fit line. This is what the computer says is the best fit line. And it has a way of doing that. I'm going to click on it and show you. What it's trying to do is it is trying to make the area between the dot and the line the smallest. It's called a squares. That's why it's called the least squares line, is it's trying to minimize the amount of space between each dot and the line. So the least squares line is your best fit line. So we can get pretty good at a best fit line. But the computer is better. The computer is better at it. So we can eyeball it, but we're not quite as good as the computer. We got pretty close. My lines were pretty close. I bet your guys' lines were pretty darn close. Because we can kind of eyeball it and we can see the trending here. But if we're trying to make some estimates, I wonder if there's a way to tell which line is better. Which is a better predictor of the data? If I wanted a better predictor of the data, would I want my dots to be farther from the line or closer to the line? Closer. So let me grab a dry marker. I'm going to draw an order. Just to give us a significantly more extreme example, because they kind of went really close together. So if I had one data set that looked like this, with a line of best fit, and one data set that looked like this. And I'm going to call this one A and this one B. Which one of these is better? A, because all my dots are really, really close to that line. This is called a very, very strong. This is a strong relationship here. They are tight together. And there is a way to measure this. The way we measure the strength of our best fit lines, how close they are together. It is a very close line. It's this R squared value. And the way you can think about this R squared value is what percent strong it is. So this one is 85% right. And this one is 80% perfect. So it's 85% strong versus 80% strong. So which of these is stronger, the one with age or the one with miles? Which one's stronger? So we could think of this one as having an R squared of like 99. And this one would have an R squared of like 20. So it's all about how percent strong it is the easy way to think about it. So of our two that we got from the computer, which one is stronger, age or miles? Age. So that's going to be the equation that it makes the most sense to use. The fact that our data is closer to the line, it's closer to trending directly on the line. So when we're looking to analyze the questions that they've given us here, we're going to use the equation for that line. Which I'm going to write out on the board over here because they word it slightly weird and I want us to practice interpreting their words. Because they write the whole thing out and instead of using variables, they pull the labels. So on our price equation, it says price equals -1,483. And then it says dollars per year. I'm just gonna write the symbol. Times age plus 24259. So I just wrote it all out in a row here. These symbols in the middle, this just tells us this is our slope. So it's not actually helping us. So I'm going to get that out of the way. I don't want that there. So my proper equation I can do stuff with is not going to have the labels for our slope. What I'm going to do instead is I'm going to say, all right, my age.
Where do we write this down at?
You can write it on the page next